Hello, good afternoon. Sorry I'm a little late posting this today, but I hope you're having a great Friday or whatever day you're watching this. So, last class we wrapped up with revisiting drawing our Lewis dot structures and drawing bonds that way. So we were looking at drawing your ionic and covalent bonds and how to show that it was being transferred or shared. Also calculating your oxidation numbers for that. So before you are done with chemistry for today, please check the answer key on Canvas to make sure that your assignment, the bonding basics assignment, is done correctly, specifically the drawings and the oxidation numbers from the table at the top. So that is on the agenda. It says review your assignment, and you can click on that link and it will come up for you. So today we're going to move on from that. The reason why we did that first, even though I know you guys have done some of that in ninth grade, is just to have a solid understanding of how to draw those, because we're going to use that today with VSEPR theory. So here again is our success indicators. So if you'd like to read through those, you can, but you will know you're successful today if you can do these things. So we talked a little bit last class about the way covalent bonds are formed, in that they are sharing electron pairs, and the way that we can draw that. So if you look on the left-hand side of the screen where we have the bonds between the hydrogens, oxygens, and nitrogens. So for the hydrogens, they each have one electron, and they're sharing the two between them, and that's shown with the circles. So that's how I was showing you or teaching you how to do that before. That can also be represented by a single line. Oh, excuse me, sorry. That can also be represented by just one dash between the two of them. So each dash represents a bond between two electrons. So if you look at oxygen in the center of that, you have a double bond because they're sharing two pairs of electrons, and you would just put two dashes there to represent that. Same thing with nitrogen. You can have a triple bond where you have three dashes there to represent three shared pairs. So then when you are drawing these out, it is best to use the dashes to represent bonding or bonded pairs, because using the circling method for molecular geometry can get messy. It can be messy, and it can be hard to see your lone pairs. So on the right-hand side of the screen, we have an explanation or example of lone pairs. So these are extra pairs of electrons that are not involved in bonding, and they belong exclusively to one atom. So in that picture, it's showing you water. So you have your two hydrogens and your oxygen. We know that each hydrogen has one electron, and the oxygen has 6 valence electrons. And within that, each hydrogen is bonded to one of oxygen's electrons. That's what your dashes are representing. So the dash is representing that oxygen is sharing hydrogen's electron on either end, which satisfies its octet rule, gives it 8 total. And then the hydrogens are sharing one electron from the oxygen as well, satisfying their octet rule because they're smaller. They only have two electrons on their innermost ring. So what you're seeing there, you have these lone pairs left over. They're not bonded. We're going to be focusing on that today because that will help us determine what the shape will be of our molecule. Okay, so we're going to talk about VSEPR theory today. It's VSEPR, so it's valence shell electron pair repulsion theory. Basically what this is saying is that when the electrons are bonding, so when your atoms are pairing up and you have all these electron pairs keeping them together, they want to try to position themselves as far away from each other as they can. So when they do that, basically what we're looking at today is going to be the 3D version versus just your 2D version of the Lewis structures. So we are going to look at the angle that these bonds will form once they're formed, and that they're trying to get as far away from each other as they can. So if you look across the bottom here, like the first one, carbon dioxide, you can see that has a 180-degree angle. So if you're looking at that carbon dioxide, you have two areas of electrons. So you have the two red dots is where you have some electrons. You have two bond angles, or two sets of bonds. So you have like one on the right side, one on the left side. They have 0 lone pairs. Okay, so for the carbon dioxide, you would end up with 0 lone pairs. So that would be linear. It would be I wish this little menu would go away down there. Sorry about that. But that's linear. And then as you go across, it just shows some other examples. So the ones that are bent, so we have like trigonal, pyramidal, and the one that is bent. Those both are different molecules that would have lone pairs. So the lone pairs are creating an area of electronegativity that's causing that central atom to have a polarity, basically. So those would be polar atoms, and anything that is linear or equal on either side would be nonpolar. We'll talk more about that. So you will find charts like this. Okay, so I provided this one. There's another good one at the end of these slides. And there's also a one with just words and no pictures that's attached to the assignment. So when you look at these, if you look across the top, you have steric number. Okay, steric number is basically how many bonds these things have. So how many legs each molecule has, if you want to think about it that way. So here for steric number, both of these just have like 2 legs. We have 2 bonds on either side, right? 3, we'd have 3 different angles coming out here. 4 has 4. So if you look at this and you might say, okay, well, this one does not have 3, but it does. So what it's representing is, if you look down here, this lone pair, okay? And I talked about that a second ago. The lone pair would exist right here at the top of this central atom, and it's causing the electronegativity to be greater right here, and it will cause this shape, okay? So it's the repulsion between these. So if you have a high electronegativity here, it's repelling these 2 angles, or these 2 electron clouds, with more force than it would here. So these would be more equal. There'd be no other external electronegativities added on. So these would form just a linear shape, and it would be nonpolar. These, like this, would be polar. So this says the steric number is 3 because it has this cloud type here. And you might also see that as, let me draw this in, something like this, where it has like a little cloud shape kind of added on to that. So this little bubble is representing these 2 dots that are there. And when you start drawing these out as Lewis dot structures, you'll see those pairs there. So erase that so we can move on. So I'm just going to go through these. Trying to get that. Wish that little menu would just stay down. Okay, so I'm going to get through these shapes and describe them for you, and then we will do some examples at the end. So what you guys are working on today to practice this is the gizmo. I did take out like a chunk of that at the end so that you didn't have 8 pages to work on, but the gizmo does a good job of showing you the repulsion between these and kind of why that happens. So what we did in class to mimic that is we put together little like ball and stick models, but I think the gizmo actually does a better job of showing that because you are shown all of the lone pairs. So with the polarity of the molecules, like I was talking about, if they're equally sharing, it's going to be a nonpolar molecule. Okay, so nonpolar being that one side is not a greater electronegativity than the other. So if it is a polar molecule, it means that you have a net unequal sharing of electrons, so that your 2 dipoles, so the 2 ends, they're at angles, which means that they're not going to cancel each other out. The force of those will not cancel each other out. So let's start with the basic ones. So our first shape, this is called linear. The shape of linear is if there's only 2 bonded pairs and no lone pairs. There's 2 examples of this here. So on the first example, you have 2 atoms. These are all those diatomic molecules. So those were on the slides from last class. So all those diatomic molecules that exist in nature as pairs, so like hydrogen gas or oxygen gas, those would obviously be linear because there's nothing to make an angle around. So those are always going to be linear. But if you have 3 atoms with 2 bonded pairs, so you have a bond on either side, if there are no lone pairs, you're going to have a 180-degree angle, and it is going to be linear and nonpolar. Okay, so there's nothing in the center there. There's nothing on this carbon atom that's causing a higher electronegativity right here. So it's going to be equally shared. The next shape is called bent. This still has two bonded pairs, so its steric number, if you're going off of that, would be 2. But these also have lone pairs. So if we have lone pairs, you would have a steric number of 3. So you have an area of electronegativity kind of centralized there on that central atom, causing the shape of that molecule to bend. So these would be polar, meaning that the one side of this has a greater electronegativity, so which in this case it's the central atom. And these are going to form angles between the bonds of 104.5 degrees. The next one up, here we're looking at 3 bonded pairs. So we have 4 atoms involved, 3 bonded pairs, and no lone pairs. So the shape of this molecule in itself makes it polar. Even though there is not any lone pairs, this one is still polar because they're not equally canceling each other out because there's 3 on either side. So these are going to create a 120-degree angle between each bonded pair, and these would be flat. So we're not looking at a pyramid shape. This would be like if you had the ball and stick model and you could lay it flat on the table. It would not be sticking up anywhere. Trigonal pyramidal would be the next one over. So this one is the same amount of bonded pairs, but we also have lone pairs. So if you're looking at the steric number, you would say that the steric number would be 4, but you have 3 bonded pairs and 1 lone pair, so you can identify it by that. These are polar, obviously, because you have the lone pairs in there. And because of the polarity, the central atom is going to be angled upward, so everything else is angled away from that, causing angles of 107.5 degrees between each bond. So we would look at this, and this would be like in a pyramid shape. So the next one over would be tetrahedral. So we're adding another atom in this one. We have 5 total atoms. We have 4 bonded pairs, so like 4 legs coming off of it, if you want to call it that, and no lone pairs. So the steric number would be 4. There are 0 lone pairs. This one is also polar because of its shape, but you're going to get a 109.5 degree angle between each of the bonded pairs. Seesaw would be next up. So seesaw is similar to the tetrahedral. It's the same amount of atoms involved. You still have 4 bonded pairs, but with these you do have lone pairs. So that's going to cause the angle to change. So these again are polar, but you're going to have 2 different angles involved here. So you're going to have a 180-degree angle across the top portion of this. So this is similar to like a linear shape. And then you have this bent piece down here. So the angle down here will be 120 degrees. So you have 2 different angles on this. You could kind of maybe think of this as like linear and bent together all in one. Next one is trigonal bipyramidal. So you are adding more atoms. So we have 6 atoms total involved here, 5 bonded pairs and no lone pairs. So these are polar once again. I don't have a 3D picture on here. I should probably add that, sorry. So these would be polar as well because they have an unequal pole of electronegativity, and you get 2 different angle types. So you're going to have 120 degrees and 90 degrees between your different bond. Last one we're going to talk about is octahedral. So the octahedral is if it has 6 bonded pairs and no lone pairs. So this would mean 7 atoms are involved. We have 6 legs coming off of it, so 6 bonded pairs. So your steric number here would be 6. There's 0 lone pairs. These would be nonpolar because they are equally canceling each other out in all directions. So this would be kind of in the shape of like a jack if you played jacks. So you have them going in 3 dimensions and they're canceling each other out equally in all dimensions. So the angles they're going to form are going to be all 90-degree angles. So here is a chart that can be useful. You might want to screenshot this or just save this slide somewhere for easy access, but you can use this to identify the shape of whatever you're talking about. So this gives you a pretty straightforward way to identify this. There's a lot of these out there, and it kind of depends on what you prefer for getting your information. So if you don't like this chart and you want to see it kind of in a different way, you can just search molecular geometry table and you will get just a ton of different examples. So they will all give you the same information. Some of them will give you the angles, some will represent these a little differently. So whatever works best for you. So when you have this, you're looking at number of electron dense areas. Okay, so this is your steric number, if you will. So your steric number for here, you have like two bonds, two bond angles. One of these electron dense areas can be an area of lone pairs. So that's something to keep in mind. So here for your geometry is going to be kind of the umbrella term for it, and within that you have your very specific names for each of these. So if we go in here and we're looking at this, we have no lone pairs. We know it has a steric number of 3. You would say it's trigonal planar. So if you go in and you say, okay, it has 3 bond angles, but it has 2 sets of lone pairs. Okay, well, 3 plus 2 is 5. So I know I'm in this row, and I would go over and say, okay, 2 of those are going to be lone pairs. Well, it must be this. It must be T-shaped. So you have options here. So these can be represented in different arrangements, as you can kind of see here. So just be paying attention to those lone pairs because they will be part of your molecular geometry. Okay, so I'm going to do a couple of examples for you guys. Let me get, I guess a black pen is not an option here. We'll just do blue. So a couple of things. So if I did one, let's say, let's do CO2. Okay, so I have 1 carbon, 2 oxygens. Okay, so I know that my carbon's going to go in the center. My oxygens would go on either side of that. So I could go through here and put all of my dots first if I wanted to. Sometimes that's helpful to put your dots in first if you can't visualize where the bonds would be. So we know that oxygen would have 6 valence shell electrons and carbon would have 4. So this oxygen needs 2 more bonds to satisfy its valence shell. So we're going to have a double bond to this carbon. And then we're going to have another double bond on this side because we know that this oxygen, it's a little messy, sorry. This oxygen also needs 2 to satisfy its octet rule. So there we have carbon. Carbon would have had 4 to begin with, and now it has 2 double bonds. So it is also satisfied. So we have no lone pairs here. So we would have a steric number of 2. So we have 2 sets of bonds and no lone pairs. So you would say that this is linear, okay? And its angle would be 180 degrees. So then if I came over here to change my color for this one, let's say I did, we can do sulfur. We'll do this one. Okay, so we have 1 sulfur and 2 oxygens. So if I have my sulfur in the center and then my oxygens on either side of that, we know that all 3 of these have 6 electrons, okay, valence electrons. So this oxygen needs to have a double bond here with sulfur to satisfy its octet rule, and so does this oxygen. But what we have left over is 2 electrons for sulfur. Okay, so we knew that sulfur had 6 to begin with. So you bonded these 2, you bonded these 2, and you have 2 left over. So what you get here is a lone pair up here. So when you're looking this up and you compared it to the chart, you would say that it has a steric number of 3. Okay, so it has 2 bonds, but it has 3 areas of electrons. So this would tell you that the shape of this would be bent. Okay, and if you were to draw like a diagram of it, it would be kind of in this fashion. Okay, a little neater than that. And then your angle here is 120 degrees. So there's lots and lots of different ways you can do these. Let me do maybe just one more. Clear that off. Do this. Okay, so let's see. We had another example. on some of the ones we were doing here. Give me 1 second. Let me just pull this up. Okay. All right. Just trying to get everything lined up on my screen. All right. So let's see. Let's do another one where we might have, here, we can do SO3 with a -2 charge. Okay, so this is a polyatomic ion. So we're going to have 1 sulfur and 3 oxygens, and then we have to add in 2 electrons because we know that if we have a charge of -2, we've added in 2. So sulfur is the only one that is by itself. So we're going to put sulfur in the center. We're going to have oxygen around it. So we have our 3 oxygens. Okay. Sulfur would have 6 valence electrons to begin with. So if we want to just put these in, and then we're adding 2, okay, because we have this ion here. You always want to add this to your central atom. So if we have this, we know that each oxygen had 6 electrons, and we need to bond it twice. So we're going to have double bonds here. Double bonds, all of these. All right. So when we look at this, these will be connected, sorry. There we go. Okay, so when we look at this, we'd look and say, okay, I have 3 bonds, 3 sets of bonds, but I do have a lone pair, so you can identify it that way. You can say that I have a steric number of 4, or I have 3 sets of bonds and a lone pair. So if I was going to identify this, I would say that this is trigonal pyramidal. This is not writing very well. Okay, trigonal pyramidal, and the bond angle between all of these would be 107.5 degrees. Is this polar? Yes, this would be polar because of the lone pair that's up there. So if you were to draw the shape of this, you would have kind of a central atom, and then like 3 legs coming off of this to try to represent your angles there. Sometimes you'll see this as a cone shape coming off. This is not a very pretty cone, but sometimes it'll be shown as a cone shape coming off of there to show that the angle, it's like angled away from you, or towards you. So as you go through these, this is what you're looking for, is how am I going to draw on these bonds? So each dash is representing 1 bonded pair. Okay, so the bonded pair of 1 from sulfur and 1 from oxygen. So here we knew we had to do 2 to satisfy the octet rule. And then if it has an ion, you would add or take away electrons as needed. So then once you get that part done, you can use that chart to identify how many bond angles it has, or how many electron areas it has, what's the steric number, and if it has any lone pairs. And that will help you identify its molecule name as well as the angle, and if it is polar or non-polar. So get the gizmo done. I would suggest doing that first and then work on the assignment. You do have 2 things to do today. The assignment, it looks like it's a couple pages, but it's really not. It just has a lot of examples and a lot of room to draw. So I think there's like 6 questions to do for that. So that's pretty straightforward, but the gizmo will be helpful in learning how to do these. So please give it a try. If you have questions, please feel free to email me. If you need to, we can set up a Zoom or a phone call or whatever. So let me know if you have questions, and I will talk to you guys next time.